How's it going, everybody? This is Ron Sparkman from Opportunity U, and today we have an amazing person to interview. I can't wait to talk to this guy. I am so interested in pretty much everything he does. This is Ethan Siegel from Starts With a Bang, and if you've not heard of this yet, once we get done, trust me, you're going to be as hooked on it as I am. So, Ethan, how's it going today?
I'm doing fantastic. You know, any day where you wake up and NASA releases a world-changing announcement is going to be a good day.
Indeed, and we'll go ahead and we have to talk about that first before we go into anything else. NASA had a huge announcement today. We found 7 rocky planets, 3 of them possibly habitable. So this is a huge thing, and what better person to talk to about it than the cosmologist himself, Dr. Ethan Siegel. So give us a little info about this, brother.
I mean, the big news is, right, we have a bunch of stars. We think the sun is a pretty typical star, and it's actually not. It's actually a lot bigger, a lot more massive than most of the stars out there. Our sun is more massive than about 95% of the stars in our galaxy. 3 out of 4 stars are the smallest class of star there are, red dwarf stars. 75% are red dwarfs. You know, you get red because you're cooler, you're lower in mass, so you don't get as hot. Right? So you burn through your fuel slower, you're smaller. This star, TRAPPIST-1, is the star we're looking at. It's only about 8% the mass of the sun. If you were to take all the energy from this star and say, how many of these stars do I need to put out the same energy as our sun? The answer is about 1,900. You need almost 2,000 of these stars. So the planets around this star that are interesting are not hundreds of thousands of kilometers away like Earth is. They're about the same distance from their star as like Jupiter's moons are from Jupiter. So what we found when we looked at this star is we used the transit method, the same thing that the Kepler satellite used. Is we're looking at this star, and when light passes in front of one of these, when a planet passes in front of one of these stars, it'll block a little bit of the light. So we'll see a little dip. Yeah. And then we'll see a rise again. We've been able to tease out 7 independent signals from this star. All 7 of them are approximately the same mass. These are approximately Earth mass planets. They're Earth mass, they're Earth size, and there's 7 of them. And that's really weird because what Kepler found is most of the planets in the universe, right, and we found thousands of them, most of them are more massive than Earth. They're what we call super Earths or mini Neptunes, where you're 2, 4, or 10 times the mass of Earth. So to find something where everything is between about 70% to maybe 120% the size of Earth in terms of radius, 7 Earth-like planets, 7 Earth-sized planets in a solar system is unheard of. We only have 2. We've got us and Venus. Mercury and Mars are way too small, yet Neptune and Uranus are way too big. So we've already got like that there are 7 of them. Now the thing is, when we look at how close they are to their sun, 3 of them are too hot for life like ours, because what we think we need, the big ingredient, is we need water. We need liquid water on the surface. So you assume if you have an Earth-like planet, and if it has an Earth-like atmosphere, would water on the surface be stable in a liquid phase? And for the inner 3 planets, the answer is that's probably too hot. And for that outermost 1 planet, it's probably too cold. But if we look at planets 4, 5, and 6, the 4th, 5th, and 6th planet from the sun, from their sun, they've all got the right conditions. We think that if they have Earth-like atmospheres and H2O on the surface, that they should have liquid oceans on half of the planet. Only half, though, because unlike our planet, which spins on its axis and half of it faces the sun at any given time, but then it rotates away from view and the other half faces the sun, these worlds are so close to their star that they're locked. Like the moon is locked to us. You always see the same face in the moon. You always see the man in the moon or whatever you see when you look at the moon. These worlds are always locked to their stars. So we think half the world is in great shape. Imagine that it took billions of years of Earth for life to take hold in the ocean and diversify, and eventually after like 4 billion years it made its way onto land. Imagine how much faster it could have gone if you were always in sunlight, if you were just continuously getting that energy you needed for life. That's what's going on 3 of these 7 worlds. Do they have life? Are they inhabited? We don't know. but I think these are incredibly strong candidates for something that I can't wait to know more about. And the star itself is only 40 light years away. So as soon as we get those Star Trek technologies, we're there.
And it really is. It's one of the most exciting times to be a space fan, and astrophysics and cosmology. I mean, there's just so much coming out, we can't even keep up with it anymore. It's what it feels like. It's just every few weeks we've got something else, another major announcement from NASA. And one of the things you do is you keep up with it. So obviously you can tell just by your excitement by this, and every time I've ever heard you speak about it, you are on fire for this. What started that fire for you with cosmology, astrophysics? What started it? What kicked it off for you?
I'm afraid to tell you, because there is a real answer to this. Like, what made you want to go do this? And the answer is, look, I always loved science. I always loved the universe, but I liked a lot of different things. I like teaching people. I like sharing my excitement about things with people. I like reading, I like the arts, I like humanities, I like music, I like a lot of different things. It wasn't until I finished college and I got my first job where I was a public high school teacher that I realized, well, this is a hard job and I don't love this. I like it and I like many of the students and I like many of the things I'm doing, but this is not what I want to do with my life. And so I did what I recommend a lot of people do. We're kind of taught in our society that it's a really bad thing to have a crisis. But I actually think a crisis can be an incredible thing. When you have a crisis, that's you saying, I am not satisfied with the direction my life is going. I need to change direction and I need to try something new. And so for me, I said, well, I'm on this side of the desk. I'm teaching people things. If there were one thing out there that I could learn, that I would just be so excited to learn, what would it be? And for me, it was, I started thinking about the whole universe. I started thinking about learning where it came from, how it got to be this way, and where it's headed in the future. And the more I learned about that, I was so pleased to realize that this is not a question for philosophers, for poets, for theologians, or for artists. This is a question for science. This is something that we can find the answer to, and we found many of these answers. So that's how I got into cosmology. That's what cosmology is it's the study of the large-scale universe, of how it got to be this way, of how it came into existence, how it turned into what we have today, and where it's headed in the future. And so I went to graduate school in theoretical astrophysics, and I specialized in cosmology, and I got a job afterwards, and then I got a research associate job, and then I got a professorship, and then I got a different professorship. And through it all, I started writing and communicating and speaking, and now that's my main focus. Is I just love this stuff so much that I can't keep it inside, and I feel like I've got to share it with everyone who's willing to listen.
And that reminds me of Carl Sagan. Carl talked about it. He's like, whenever you're in love, you've got to tell the world. And I understand the crisis completely. I was a professional DJ for a long time, and then I was going through a really, really rough time in my life. And then I watched the new Cosmos, and I had never thought of the universe in that way. And by the time that it was over, once I realized how big the universe could be, what the multiverse could be, what these things could be, there was no way I could go back. When that first commercial hit, that was it. I was done. I was like, this is what I've been focused on for so long. This is a Simpsons commercial. I would love to watch this. This is what I would normally be watching. And look what's out there. And I think that's for so many people, that's what happens, is that one day we just wake up and realize there's so much more than this little tiny worldview that we had. And it's amazing to see what you've been able to do with it. And it's really something you have taken to a whole new level. You talked about your writing, and we're going to get into that in just a few minutes. But first up, so you went into theoretical cosmology, and you in particular went into cosmological perturbation theory. For those that don't know what that is, can you explain it a little bit in layman's terms?
Yeah. So if you imagine, I'm going to ask you to imagine the Big Bang, and that's a tough thing to imagine, right? Mm-hmm. So I want you to think about the universe when it was very, very young. It's very different than it is today. Today, the universe is full of galaxies separated by millions of light years in most cases from each other. And each galaxy has a whole bunch of stars, like billions or trillions of stars in there, separated again by light years. So you have these big clumps of matter separated by these great distances where there really isn't anything to see in between. In the early universe, right after the Big Bang, it's not like that at all. It's extremely uniform. The matter density, the temperature, the radiation density, it's almost exactly the same everywhere we look. But it's not perfectly the same everywhere we look. There are tiny, tiny differences. That's what a perturbation is. If you're in a region that's a little bit denser than average, and by a little bit, I mean less than about 0.01%, so only less than a part in 10,000. But if you're a little bit denser than average, then you're going to preferentially start to attract more and more matter to you. And over time, the more matter you attract, the bigger your gravitational force gets and the more successful you get at attracting extra matter. So that's where these overdense regions are going to grow into stars or galaxies or groups or even clusters of galaxies. The underdense regions, if you're less dense than average, you're going to give up your matter. You're going to give it up to the more dense regions. So you're going to become less and less and less dense. You're going to become what we call a cosmic void. You're going to be a region that doesn't have stars or galaxies in them, or at least has far fewer than average in them. And so what cosmological perturbation theory is it says, we know what the universe looks like today, and we know what the universe was like very early on. It was almost perfectly uniform, but not quite, and it is extremely lumpy and clumpy today. So how did we get from the early smooth universe to the modern clumpy universe? That's what I studied, is how the universe went from what it was at the Big Bang to what it is today.
Fantastic. And if I'm correct, that's actually what the James Webb Telescope that's coming out next year is really going to kind of help us answer some of those questions, looking back sort of to the beginning of that 200 million or so years when actually those stars started to ignite and those things started to kick off. So I know you're going to be excited about that. And I mean, you know, that's what you're doing all the time now.
Well, I mean, look, I wouldn't be doing what I'm doing if I wasn't still so excited about it. So I told you about that crisis I had, and what year is it now? 2017. So that was almost 17 full years ago now that I had that crisis. So yeah, I went to graduate school and I got my degree and I had the career path that I had, but it's led me to this, and this is what I'm doing now. And I'm so excited to still be talking about it, to be keeping up with the cutting edge of what science is doing, and to be sharing the knowledge and excitement that I've gained with anyone who's willing to listen. So yeah, when you talk about the James Webb Space Telescope, the thing is, we can look back into the distant universe as far as our telescopes will take us, but they're limited by two things. They're limited by how big they are, which is how much light they can collect, and they're also limited by what wavelengths of light they can see. So if you look at the universe and you say, okay, I want to know where starlight comes from. Well, starlight is mostly visible light. If I look to the very distant universe, I have to remember that the universe is expanding. So what determines what light you can see? It's its wavelength. The wavelength of light determines what you can see. We can see blue light, you know, violet, blue, all the way down to orange and red, but we can't see longer wavelengths than red because that's infrared and our eyes aren't adapted to that. And there are shorter wavelengths than violet, that's ultraviolet, but we can't see those. So if we're saying, I want to look at visible light, well, you can only see that a certain distance away, because at some point you're far enough away that the universe has been expanding and all your visible light has shifted into the infrared. So what makes James Webb Space Telescope so exciting is it's not just huge, it's 7 times the area of the Hubble Space Telescope, which is the largest space telescope operating telescope. We, human eyes, can see between 400 and 700 nanometers. 400 is violet, 700 is red. That's the limit of what we can see. James Webb Space Telescope is going to start at about 500 or 550, so right in that yellow or maybe even chartreuse region of the spectrum. And it's going to go all the way to 30,000 nanometers. Wow. So it's going to be able to see wavelengths of light that are many, many times longer than what the human eye can see. It's about 40 times longer than what the limit of human vision is. So that's why the James Webb Space Telescope from up in space with that giant mirror is going to be able to see back to, such great distances. The universe, we think, based on perturbation theory, should form the first galaxies sometime when the universe is maybe 200 to 300 million years old. And that corresponds to a distance today of 30 some odd billion light years away. James Webb Space Telescope should be able to see definitely galaxies as early as 275 million years ago from when the universe was 275 million years old. That's a distance of about 32 billion light years, but it might go even further. All right, we have to see, but that's what I'm super excited about, because it can see this ultraviolet light when it was emitted that gets shifted through the visible part of the spectrum into the infrared, maybe even into the mid-infrared part of the spectrum. So that's what we're looking for with James Webb, and it launches next year. So this is not some, you have to wait decades for it. Like, no, This is on the horizon. October of next year. I can't wait for it.
and I would have to agree with you completely. I mean, it's going to change everything. And, it's just, we continue to see all these advances, and it's something that you were really great with. It's what you're always keeping people up to date with. You started with your first book, Beyond the Galaxy, and that really kind of seemed to open the door for you when it came to showcasing this ability for science communication. And now you have Starts with a Bang. People can read it on Forbes. You can read it on Medium. You have your own website, and we'll, definitely drop those links a little bit later for everybody to go and subscribe and check it out. But what keeps you going? What are these interesting topics? How do you come up with them, and what do you decide to cover?
It's really funny that I think a lot of people ask me that, because I think a lot of people who write, they're always looking for a story, and I have to always pare down. I have the opposite problem, because at any given moment in time, I have just dozens of things that I want to write about, where I'll be reading something, or I'll be thinking about something, or I'll be talking to someone, and I'll be like, oh, wow, how do people not know about this? How do people not know how stars work, or how planets form, or how we got our moon, or how Mars used to have more moons than it has now, or how, like, all of these things are just, there's so much that humanity knows. There's so much that the experts in any given field know that most people don't know. And that knowledge usually gets, scoffed at, like, oh, those are for ivory tower elites, or those are for, like, just a few people in the universe and on Earth who've bothered to study this esoteric stuff. And I think that's a terrible way to look at things. I think the universe and everything we know about it should be accessible to anybody who's curious about it. And so that's kind of been my mission that I've taken on, is I want to tell people what's out there right up to the cutting edge of what we know. I don't want to dumb it down. I don't want to leave out details, but I just want to say it in plain English. I want to tell you the story without making you do the math, because we can do the math, and I can do the math, and if you wanted to, you could do the math too. But that isn't necessarily going to get you that much more knowledge. If I can give you 95% of the details in plain English, and you can learn it by reading a 5-minute or a 7-minute article instead of a 5 or 7 year education in graduate school, wouldn't you rather do that?
And there's plenty of people that are, and you're seeing science communication has become this huge, massive thing now. You've got leaders like you, and there's people that are kind of approaching it from all sides, astrobiologists. And of course, you've got the big names like Neil deGrasse Tyson, Carl Sagan, but even more people are coming up, and regular people can do it. I'm personally in school for it. I've got 10 years ahead of me, but as long as you're telling it and you can understand it and you're expressing it in the right way, people want to hear more about it. It's almost magical. Whenever we think about these things, the reality is so amazing, we don't need to make things up, but people need to hear it in a way that they can understand it. And sometimes they're spoken you know, it's kind of spoken above them, but you figured out a way to really be able to discuss it with these people and tell it in a way that they can really connect with. And that's what's so fantastic about it. And, you know, there's so many things that you cover in these articles. So we've got a bunch of them to go over. So we'll go ahead and dive right into that. So Forbes is how I found you. You know, I was checking out your work. And this is one of the big topics that's been going on. We've heard so much about this. There are a lot of people that believe that the world is flat, that the earth is flat. So what's one of the ways that the average Joe can test in the real world to see that the world isn't flat?
Well, so when you talk about ways to test, right, there are all sorts of things that most of us are actually kind of familiar with. Like if you go to the ocean, if the world were truly flat, you'd be able to see across the ocean because you'd be at a higher elevation at your eye level just from standing up than any place on the ocean. So you'd be able to see the other coast no matter where it is. But you know you can't do that. You can't do that at the ocean. You can't do that at the seas. You can't do that at many lakes. You can't see across it. Because from your human perspective, even if you're a tall person and your eyes are maybe 2 meters off the ground, you can only see for about 6 or 7 miles until the curvature of the earth hides something from view. So one of the old arguments that people used was, well, if you see a distant ship, right, you first see the mast of the ship above the horizon, and then you see the deck of the ship and the bow, and finally you see the whole ship as it comes towards you. And if it goes away from you, you'll see it disappear the same way. That's indirect. If you want to do it directly, let me tell you how we first proved the earth was round 2,300 years ago. So there was this guy, Eratosthenes, and he was a Greek living in Egypt. And he was living in the town of, oh boy, I'm going to forget. I believe he was living in Syene, which is above the Tropic of Cancer. So it's north of the Tropic of Cancer. It's close to like the Nile Delta. And he got a letter from someone further south. And the further south person said that on this day of the year, it was the summer solstice, on this day of the year, if I plant a vertical stick in the ground, it casts no shadow. And Eratosthenes was like, that's crazy. Sticks always have shadows, even if they're totally vertical. So he planted a stick in the ground, and on the solstice, he measured its shortest shadow. At high noon on the solstice, he measured his shadow, and he got about 7.2 degrees was the angle that it made.
Mm-hmm. Yeah.
And then he did what a good scientist does, is he went down to that place the next year. He went down to Aswan, and he said, I'm going to measure this. And sure enough, sticks cast no shadow. If you looked down into the well, your head would block the sun from above you because the sun would be directly overhead. And he realized that, oh my, the earth is shaped like a sphere. And the farther away in latitude I go from the equator, the bigger my shadows get on the solstice. So he went even a step further than that 2,300 years ago and said, I'm not just going to say the earth is round, I'm going to measure its circumference. So he said, look, if I know the angular difference between these 2 points on earth, what I can do is I can measure the difference. And then if I know the relationship between an angle and the distance, I can compute the circumference of the earth. And he single-handedly, by doing that, invented the field of geography. He wound up mapping out about a third of what's now Europe and Asia. He wound up concluding that there's a hot zone on Earth at the equator, 2 temperate zones at the mid-latitudes, and 2 frozen zones at the poles. And he figured all of this out 2,300 years ago using camels to measure distance, because that was the best technology at the time, and sticks with shadows.
And see, you know, we think about all this technology that we have nowadays to do these amazing science things, and you don't, camels and sticks, you know, sometimes you got to use what you got, and, you know, necessity is the mother of invention, and look what he was able to figure out. And,
And that's the big thing is, you can say, all right, Kyrie Irving or whoever the latest person who thinks the earth is flat is talking about it. Like, here's the thing. What would it take to change your mind? What would it take to prove to yourself that the earth is actually round? Because you can do that. You can prove to yourself that the earth is actually round. You just have to ask yourself, what will it take to convince you?
And can you be moved? And that's what we have a lot with so many people nowadays. And that's actually one of the questions we're going to get to in a little while of scientific method and what it can really do for you. But you recently wrote a really cool article talking about, all right, so the Earth's not flat, but here's a way that we could possibly create a flat planet, or there's could kind of be something like that out there. Can you tell us a little bit about this idea? Because it was a really fun article to read.
So I was thinking about this, and it's you can't have an actual flat planet, because in order to be a planet, the number one rule is you need to be massive enough to pull yourself into hydrostatic equilibrium. So if you say hydrostatic equilibrium, that means, if you're not rotating at all, that's a sphere. That's a perfect sphere if you're not rotating at all. But what if you did rotate? Well, then you get compressed at the poles and expanded at the equator. This is actually true on Earth. Our rotation that we spin around once every 24 hours, you might have learned in school that if you drop a ball, it accelerates down at 9.81 meters per second squared. And that's the acceleration due to gravity. That's not the acceleration due to gravity at the poles or the equator. It's actually 9.83 meters per second squared at the poles, because the poles are compressed, so you're closer to the center of the Earth. And at the equator, you get a bit of a bulge, so you're further from the center of the Earth, and it's actually 9.79 meters per second squared. Now, we have lots of worlds, lots bigger than Earth, that rotate a lot faster than Earth. Saturn in our solar system rotates with just about a 10 or 11 hour day. If you were to say, how many Earths can I fit across Saturn? If you went across Saturn's equator, you could fit 11. But if you went from pole to pole, you could only fit 10. So if you see pictures of Saturn and you're like, it looks a little squished, it is, because it's spinning. The most extreme world we've discovered is called Haumea. It's out in the Kuiper Belt, and it spins so fast that its equatorial axis, its long axis, is twice as long as its polar axis. So it's about 2,000 kilometers across at the equator, but from pole to pole, it's only about 1,000 kilometers. So if you wanted to say how flat could a planet get and still be a planet, you can get maybe a 3 or 4, or if your planet was made of something crazy like solid uranium, maybe you could get even a 5-to-1 ratio, but you could never get it perfectly flat. That's the best you could do.
That is fascinating, and it's something that I've never even heard anybody even discuss. Because as soon as anybody hears flat Earth or anything about a flat planet, they always completely change it. They roll their eyes and say, "Of course not," and move on. But it's kind of those ideas that you dive into. You try to go into the other side of things. Everybody.
Part of the way I do that is, I didn't always know this stuff, and I didn't know much of this stuff for a very long time, but I remember what it was like to learn it. And so if I can understand where someone is coming from, like, how did you think your way to your current position? How did you logic yourself into this position? Then if you did logic yourself into it, then maybe the right approach and the right way of thinking will get you to arrive at a different conclusion. Now, if you didn't logic yourself into it, if you just arrived at this position because I believe this is this position and nothing's ever going to change my mind, well, then nothing's ever going to change your mind. But I'm still going to try. I'm still going to try to present you with the best factual argument I can to try and say, well, if you decided someday to approach this problem with, I don't know the answer, what questions would I ask and what line of thinking would I go down to arrive at the answer, then maybe someday you'll get there too.
I love it. And, like I said, you really kind of go over so many different ideas. And, sometimes you come up with cool ideas that people hadn't thought of. And sometimes you kind of want to make sure that people are brought down to earth a little bit. And speaking of which, one of them is that everybody's really kind of talked about super Earths, thinking that super Earths are going to be the places that we are going to find life. But in one of your recent articles, you talked about it, that science is really kind of telling us different. So what assumptions are people making about what these super Earths are going to be like? And how could they rethink that, kind of like what you were talking about with their thought processes? How do we bring it back in a little bit?
Well, if we look at our solar system, right, the biggest rocky planet is Earth. And the smallest gas giant world is either Uranus or Neptune, depending on whether you're looking at mass or radius. But Neptune and Uranus are both about 4 times the radius of Earth. And they're also about 17 times the mass of our planet. So it was a bit of a surprise when the Kepler spacecraft turned up that actually the most common class of planet in the universe is between 2 and 10 times the mass of Earth. It's either called a super Earth or a mini Neptune, or some people break them up so that you have super Earths and mini Neptunes. But we know at some point you're going to hit that dividing line where you're suddenly massive enough that the thing that separates a gas giant from a rocky planet isn't the rocky part. All of the gas giants in our solar system have rocky cores at their center. So they're all at their core, very super Earths. The thing that separates a gas giant from us is a gas giant can hold on to the lightest gases in the universe, the lightest elements. They have giant extended envelopes of hydrogen and helium. And that's what makes them a gas giant. So when you hit that threshold where Earth's not massive enough to hang on to a hydrogen and helium envelope, but Neptune and Uranus and Saturn and Jupiter are massive enough. So if you turned up the mass of Earth more and more and more massive back when the solar system was forming, you would find, what? At some point, I hit that threshold where suddenly I start to hang on to my hydrogen and helium. And if I hang on to that, then I can hang on to a big extended envelope of it. Those types of worlds where they have that gas giantness to them, they're not very good for life as we know it. Sunlight won't be able to reach the surface. You're going to have tremendous atmospheric pressures. Instead of the pressure we have at our surface, you're going to have thousands or tens of thousands or maybe even millions of times the pressure we have on Earth. This we don't think. Look, I'm not going to rule out the possibility that there could be life there, but it's not going to be life like you and me. It's going to be a very different type of life, if it's life at all. And so what the scientists did about a year ago is they said, we've got masses and radii of enough planets. They had about 300 or 400 that we can actually plot what is the mass, what is the radius, and what does that mean for density? And what they found is that there's a nice relationship between mass and radius for all the rocky planets up to about twice the mass of Earth. And twice the mass of Earth is only about a 20% bigger radius than Earth is, 20 to 25% bigger. You get bigger than that, and you start to hang on to the hydrogen and helium, and you become a gas giant. So what we're thinking of as super Earths, 2, 4, 10, 15 times the mass of Earth, these are gas giant worlds. These have a big hydrogen helium envelope. These are not going to have thin atmospheres with oceans on their surface. These aren't going to be worlds like ours. So that was a big discovery that we really only just learned enough about last year to say, you know what? We think we have the answer to this. And you might not like it, because when we discovered these new types of planets, we were like, oh, our solar system is weird. We don't have any of these super Earths. That's actually not a good way of classifying things. You have rocky planets like Earth. You have gas giant worlds like Neptune. And then you have really big gas giant worlds like Jupiter. And then you have stars. And those are the 4 classifications that we should have, and that's pretty much it. So if you're like, yeah, we don't have any super Earths, I'll tell you, I don't really think there's any such thing as a super Earth.
And see, that's really cool. You're clarifying these things that sometimes these buzzwords happen. Science is even